everybody. My name is Slava. I work at the Columbus Collaboratory as a data scientist. I have a background as a statistician. Columbus Collaboratory is a pretty cool company. I do a variety of sort of analytics projects there, building mathematical models, deploying them, integrating into product. Lately, I've been working mostly on cybersecurity. And as sort of in that vein, I've been looking into this AutoML thing recently. Went to kind of a little boot camp with DataRobot, which is a big kind of company in this space, and wanted to sort of record a few thoughts and observations and sort of conclusions that I've gathered by examining the space and sort of shared with you today. As you probably know, sort of ML is one of these massive trends that are happening right now. And it's really driven by kind of a few things. I mean, one, you have this Moore's law that's been kicking for the last 100 years, really, and just giving you more and more compute. And historically, automating calculations was really difficult, right? Either machines didn't exist, or you had these mechanical calculators that could only add and multiply, maybe divide. You know, they're very limited. Today, and for the last 100 years, things have changed a lot. The other piece is data. Historically, also, measurement instruments were very delicate, very simple, were mostly only controlled by scientists, and scientists also almost didn't exist, right? So data was a kind of a very rare commodity. And in today's world, sort of data is coming out of everywhere, right? There's sensors, everything that gets digitized, you can think of basically as being data now. From sort of websites to interactions to human files, to transactional data that's coming out of businesses. And of course, there's more and more cameras and Bluetooth sensors that are being plugged in and all kinds of other stuff. So data is coming in. The other big thing is actually research, right? So more and more researchers and universities are kind of blowing up with people for the last 100 years. Papers are being published, and there's all sorts of activity across the fields that sort of bear on machine learning and sort of modeling and data. And this is just a chart from archive submissions kind of over time, and you can see these trends just like in other domains. And the last thing is software, right? So to actually take advantage of all this stuff, and this computing and data, you gotta have the software. And this is kind of like the developments in the last maybe 7 or 8 years, really. A whole bunch of frameworks, really well built, really efficient. Most of them are in C++. Really powering, making it easy. You don't have to read a paper and then code things yourself. If you've ever done it, you've probably experienced a lot of pain and a lot of trial and error. Mathematical algorithms are kind of hard to code. So all of these trends are sort of powering ML, right? Of course, if you look at these charts, it's like they're like a few years old. It appears like things started like in the last decade. I mean, in reality, this has been a thing that people have been yearning towards for a very long time, right? I mean, these are just a little example here. Blaise Pascal from 16th century, writing. This is Fermat writing a letter to him. They were corresponding about the concept of probability, back in 17th century. And this machine over here on the right is called a Pascaline. Is one of the first mechanical calculators built by the same guy because he was tired of doing basically addition and multiplication by hand. And most math could basically be reduced to addition and a few functions if you look at it closely enough. And of course, throughout history, I mean, these yearnings, they began in a variety of places, but some interesting examples were like in ancient Greece, for example, Aristotle thinking about the radius of the Earth, and there was some pretty interesting data that was collected in Greek islands and in Egypt about the shadow of trees at different times of the day, from which you can actually get an estimate of radius of the Earth through a very elaborate geometric argument. People, of course, were thinking, looking at the stars and trying to calculate orbits of the planets rigorously, at least since Kepler. You have governments collecting census statistics, right? And doing all sorts of population sort of kind of calculations, like how many men and women do we have, how big is our, how much property do we have, all kinds of stuff like that. How many taxes are we collecting? Gambling, right? The Fermat Pascal correspondence had to do they were actually commissioned by a wealthy guy to figure out how to win at gambling, right? That's sort of the origin of probability, because if you calculate the odds, you can place the bets better, and the expected value of your bets is going to be higher than if you just kind of follow any other strategy, really. At the same time, about 100 years after that, you have navigation and insurance, right? So the early stage of capitalism, merchants are going to Asia, bringing in spices, basically arbitraging the markets, right? Buying something for cheap, selling it for higher price. Doing voyages back in the day was a really risky business. If I invest money, that's why it's called a venture, right? An adventure. And navigation was also very difficult, because if you've ever been in the sea and you look around, it's really hard to orient. You have no idea how to do it. And so some of the early sort of applications of mathematical modeling were both for navigation and, as a result of that, for insurance, to insure the actual ships. And of course, as you kind of get into more modern era, you have things done in agriculture, to amplify yields of crops. And of course, once you have the factories, you can think about quality of production on assembly lines. This is just a small sample of these forces of data and algorithms and computers coming together, sort of powering a variety of applications. So what's interesting about today is that people who are sort of in this space, they're not only doing, they're really creating, in some sense, software, right? And what ML is doing is kind of making people to reconsider, like, what is software and how do you build it? And there's a sort of conceptual framework of, we kind of write algorithms more traditionally, if you're able to imagine sort of how do you go from input to output and all the steps in between. And that's a kind of a domain where you have inherently deterministic problems. The errors are unacceptable. You have little data or hard to collect data. You are able to guess the complete algorithm and then potentially iterate over it to get to the correct version of it or the efficient version of it. And the guessed algorithm is in some domains could be practically unfeasible or underperforming. And then because of this machine learning thing, right, people are thinking that, okay, the output of the machine learning programs is just another program. So it's just another way to write software, really, right? But it has different characteristics, a different process. It's a different set of kind of skills that you have to employ. It's inherently probabilistic, right? The errors are okay, and errors are actually inevitable, right? It is typically arises in domains where data is abundant or is easy to collect. Advertising would be a great example. Like, what's the probability that if I show you this banner ad, you're going to click on it, right? That's Google's business. It is also very useful in domains where it is really hard for you to actually guess the algorithm. So image analysis has come up as a great domain where if I show you an image, how do you come up with the steps to turn that into to figuring out what the outline of an object is? Like, if I'm looking at you, I can sort of do it, but how does the computer able to detect everybody here in the room and draw an outline around your body? Like, what are the steps that you are going to write down? It's a little hard to imagine the actual algorithm. And historically, people have tried to imagine them. They didn't really work well. So given that, these are actually interesting charts that I borrowed from Andrei Karpathy, who is a director of AI at Tesla. And he was talking about the actual code for their vehicles. And he said that we started roughly over here on the left. Most of the code stack is sort of traditional C++ stuff. Like you said, of course, the vehicle is really just a kind of a computer now, right? Where you have a bunch of sensors, information is constantly pouring into it, and it's running all these models to detect people, to track people, to detect lanes, all kinds of stuff, controlling the windshield wipers. And one of the things that he noticed is that, yeah, this makes a lot of sense. We have this kind of a mixed code base. But over time, he noticed this, that this software 2.0, basically predictive models are creeping and taking over the code base, right? So if you look at the stack, it's kind of peculiar, right? And in order to sort of do this 2.0 kind of code, it's all about data. You know, he was like, in graduate school, I cared a lot about models and algorithms, and when I'm in Tesla, mostly I care about data. And this is the shift. This is the kind of shift from the software 1.0 to software 2.0. You have to get one of these kind of a statistical hat, right? You want to think about data collection. You want to think about experiments. You want to think about signals in data. You want to think about regularities, right? Sort of statistical concepts like that, because that's how these models are built. And the other sort of way to think about it is, as opposed to writing out the steps for the algorithm, what you're creating are these search spaces. You're creating a search space, like this blue bubble over here. And what happens is you ask the computer to optimize within this search space, right? It will find what the steps should be to connect the input into the output. So it's about optimization. Optimization is ultimately a mathematical problem. It's about derivatives. It's about local minima and maximum, concepts like that. So all of that sounds difficult, and generally people who get into that have some kind of data science sort of background. And this is one representation of the kind of steps or tasks you have to often get involved when you're dealing with sort of software 2.0 or just creating machine learning models. You got to get the data actually from somewhere. Typically, it's messy. The names are all off. The data types are all off. They're missing values everywhere. Things are disorganized. There's data, hiding in spots where it shouldn't be. So you have to do a lot of sort of tidying. And then you have these additional peculiar skills like visualizing things, right? But you're looking for patterns in them, doing various kinds of statistical transformations of the data, sort of building models, and there's a lot of looping in that cycle. If you do a master's degree in stats, this is the kind of stuff that you sort of learn there. And of course, there's at some point, once you go through one of these cycles and you want to deliver this model in some form or another, it could be in a report, but more and more often now, these are APIs that are being deployed on the cloud or something like that. They could then be integrated with your application or somebody else's application, right? So do you really need to do all that or learn all that to actually take advantage of sort of machine learning? Not really. What happened in the last few years are more and more interfaces to it have developed. And these interfaces, it's almost like the learning curve used to be almost like vertical, and then you had to go really, really steep, right? Start with math, build up your knowledge. If you go to like a stats program or like a machine learning program, and well, you begin with set theory. You begin with sets, intersections and joints, and then you have probability to it, and then you add, there's all this, the philosophy is build it from the ground up. That takes years of knowledge gathering, basically. And how can you take advantage of this without actually going through the whole program? And so several interfaces have developed. One is APIs. So IBM was probably the first one with this thing. They started building useful, capturing models that work with text, for example, text classifiers, that work with images, for example, how do you segment objects in images, or sounds, how do you do, for example, speech to text translations. And they just build up models on massive data sets and expose them as APIs. You submit your image, we tell you what's inside of it. You don't have to know anything about machine learning. It's just an endpoint that you hit with your data, right? That's top level, highest level sort of access as a developer. There's this other layer that's been developing, and that's kind of the focus of my talk is this AutoML thing, right? So sometimes canned models are not enough. You have your own data set, maybe you want to optimize on it, maybe you have your own set of classes. The canned models don't have the objects and images to detect, right? Maybe you're flying a drone, and the drone is surveying some kind of a construction site or fields, agricultural fields, and looking for plants, for example, that have disease on them, right? This is the kind of thing that there's not going to be just an API that you hit for that. You have to build the model. So AutoML, and I'll go more into that, is the one step down into the details. You still don't have to do a whole bunch of math. Actually, no math really. You're just playing with algorithms. What you're trying to do is, this is my problem. I have a classification problem. I have a ranking problem. I have some kind of a quantity I want to predict. And this is a family of algorithms that just solves that problem. How they work doesn't matter. Just pick one. It's a kind of a pattern matching almost. And it does all the details behind it's all automated. Then, of course, You say, well, those are not enough. I have this peculiar problem. I have these special assumptions in them. I have to really develop potentially, do more sort of custom things, custom data prep, maybe modify the hyperparameters somehow, take more control. And there are these really great open source libraries like XGBoost that just give you access to model building without, again, a whole lot of math. And then if you want to go on this next step, right, you have libraries like TensorFlow, or you have just environments like R, or just Python with NumPy, where everything is allowed, right? You're back in the math world, you're back in building, right? You're back in just putting the atoms together. So this is nice, right? Because the learning curve isn't anymore like you're on the floor and all of a sudden you have to just jump on the mountain, right? There are now these little steps that you can take. And the more you invest, the more you get out of it. So I'm going to talk about this second layer over here, because that's the kind of a trend I've been sort of investigating recently, and there are interesting things in there. So what is AutoML? It has sort of two goals behind it. One is, how do you get access to ML to non-experts? That's one goal. The other one is, how do you make sure that you get a pretty decent model for your data and deploy it, right? Because the value really starts coming when it's running somewhere and it's getting inputs and sending out outputs on a continuous basis, right? Those were sort of the objectives behind it. And what it saves you from, as I was sort of saying, is this kind of stuff, right? You don't have to think about the actual constructing the equation for the optimization problem. You avoid all this. You don't have to think about how to minimize your error by controlling the complexity of your mathematical model, right? This is kind of what statistical sort of theory works on. It basically does the search for you. It just tries a whole bunch of different models, and you want to be over here, and it starts sliding around this thing until it finds roughly this spot over here, and then it stops, right? So you can think of it as a search problem. Underneath, it basically generates blueprints like that. This is a software called DataRobot. So if you open up the box a little bit, it'll show you this is kind of what's running in the background. And typically, these things are, your data comes in, it breaks it up into types of variables, like categorical, numerical, or text. It does all this data prep. A lot of this is sort of very practical knowledge that you gain as a data scientist by just brute forcing through a bunch of projects, little tricks of trade, so to speak. They capture a lot of the encode, and then they pass it into a really flexible sort of family of equations over here. And these arrows, they basically define different combinations that they're going to try. They don't know what's going to work best in practice, and they don't want you to think about it. We have so much compute, we can just run a bunch of freaking models on the cluster, and we'll just brute force through it, right? And in the end, you get your model, and you can generate predictions, right? So templates like that. And this is kind of a nice diagram. I mean, ultimately what we want to do is AutoML tries to capture some of the so-called feature engineering, basically turning raw data into a mathematical representation, and then search through a bunch of models over here, such that it optimizes on some metric that you like. Prediction accuracy is one, and applied context, you really want to think potentially dollars maybe, right? If you want business impact or some other metric that makes sense. And it pushes you towards production, right? So you have some kind of a server dedicated to receiving inputs, sending out outputs. Because ultimately, we want to integrate this thing into the overall software stack, into the overall application, right? Make it available as a service to others. Kind of like in Tesla, as you saw, the little blue bubble and the red bubble, right? An integrated system. Why does it work? It builds off on a very important principle, that there are no universal algorithms. There's no one thing you can write down that solves every problem in the world. It's a very important thought. People yearn for one solution to everything. It's a very comfortable thought. You just come up with one theory, explains everything, right? One algorithm solves all the problems. So there's this little bit of math that basically shows that any model, on average, will basically randomly predict across all the possible data sets out there. So you build it on one data set, and if you calculate its performance across all the other data sets, an average is basically guessing. And that's every model. And from there, sort of the logic develops, well, there's no universal model. What you have is something like this, rather. You have to take the considerations, the constraints of your particular domain. Something about the relationships between inputs and outputs. Are you in medicine? Do you know something about genetics, right, that you can take advantage of? Are you in brain science and there's something about the connectivity patterns inside your brains? Are you in business and there are some constraints that come from operations in the factory, right? All of that background and contextual understanding is what allows you to build specialized algorithms that actually perform really well, that actually solve problems. Versus some sort of a general purpose model that in the end just basically doesn't do well on any problem. It's a very, very important thought. What this pushes you though is that AutoML and all these different products that are coming out, they're trying to focus on certain kind of things. Things that occur frequently in businesses, in applied areas, and things that we understand pretty well how to solve now. And once you have those two components, that's how automation starts coming about, right? We have constraints, we have understanding, we see a pattern repeating itself. Let's automate that. So one pattern is data. If you ask people, what kind of data do you have access to? Typically, it's so-called relational data, just tabular data, right? It's sales data, it's transactions, you know, it's advertising, it's a lot of business operations, basically. It's government data, census data. A lot of it is like this, tabular. And a lot of text stuff because of websites and emails and text messages now, and Twitter and so on. And things like image and video is like, except for a few companies, almost nobody's doing these things. You know, startups are of course are doing stuff like this, but in general, overwhelming number of data scientists just work on still tabular data sets. That's where most economic value really sits, at least today. If you actually ask in terms of bytes though, it will flip. If you ask how much storage is taken up by the different types of data, it's going to be like overwhelmingly video and image now. So we have these high resolution sensors, just constantly everybody's taking pictures, recording stuff. In terms of storage, but so you have to kind of consider whether what we're measuring is just sheer amount of storage footprint or variability of domains across which the data spans, and therefore the variability of different applications that you could impact. And relational data just covers way more areas, even though the data sets are much smaller. The other piece is you have kind of standardized form data sets. We'll focus on tabular things here. And you have these several model families that have been developed, as XGBoost, for example, or pretty simple neural nets that just keep on working. And they work really well within these constraints. So what AutoML is about is, if I have this kind of data, I can use this kind of family of algorithms, and generally it will do really well. That's the thought behind it. So who is offering all this stuff? There are cloud providers. So there's AWS SageMaker, Google AutoML, Microsoft ML Studio, and then there's several sort of platform companies, DataRobot, H2O, and Able. So there's quite a bit of competition now. They vary in their strategy, they vary in how mature they are, they vary in how many types of data sets they fit. For example, DataRobot is overwhelmingly deals just with structured relational kind of data, and Google AutoML has some image stuff just because of all their investments into image data. So let's look at a couple examples. I set up a little account with Google Cloud, and I pulled down two data sets from Kaggle. Kaggle is the big competition platform in data science. People basically upload data sets, often put a price tag on winning, and there are competitions. 20K, 50K, 100K, depends. Companies are doing prototyping like this now. It's very interesting because you throw a data set out, you put in 50K, you have like 1,000 teams are looking at it with a lot of skills. And what you buy is basically their code, right? It's very cheap. It's much cheaper than a consulting company of some sort, if you think about the numbers. So what do I have? I have to, so when you set up the AutoML, I'm just going to pick Google Cloud because it has the simplest interface, and simplest also means most opaque, right? It removes all the details, right? It's a really good abstraction. I have these two data sets here. One has to do with text messages, trying to identify whether it's spam or not. I don't know about you, but I get a lot of text messages of spam. Links and people asking me for money and all kinds of stuff. The other one is sales, right? Structured data. So in spam, so you basically have two columns there. Let's see, what does it show here? Yeah, just has two columns. So the first thing you would do is like just import it. I'm assuming that's kind of prepped. You can point it to BigQuery. You can point it to cloud storage. You can lift it off your computer. That's what I did. And then you specify where you want to stick it. You have the schema for it. So the schema is important to think about, specifically the data types here, where the data types are not necessarily like computer science data types. They're more like statistical data types. Because of that blueprint thing that I showed you before, for each data type, it does the special preparation of data to make it, to turn it into a mathematical representation. So it's kind of that sort of data type. And in this case, we have this categorical one, which is it ham or spam? And then you have the text, which is the actual text message, right? So the other thing is what you have to pick is just the target column. So all of this, what I'm working are basically regression models. If you've ever done any regression analysis, simple linear model, you have X, you have Y, you find the relationship between them. I give you a new X, you give me a Y. That's kind of it. In this case, our X is text, and our Y is a category, whether it's ham or spam. Very simple. Basically 2 dimensions. And the only thing that it asks you to do is to say, well, what are we trying to predict? In this problem, the initial thing to predict, of course, is ham or spam, given a text message. It's just like the old email spammers, right? Like I read your email, I'll tell you whether to put it in a junk box or not. Same concept. The nice thing that it does, this whole environment, all these environments do is they actually impose a workflow. So if you're coming into this, don't have the background, don't have the degree, this is nice. It gives you structure, it gives you stages, and there's a lot of things that are automated, but also a lot of good sort of quality controls. And one thing that you need to do, an important thing to do is data splitting. What is data splitting? So you have a sample of data, you want to build your predictive model on it, you shouldn't build on the whole data set, right? You want to, in order to actually test how well it does, you want to leave a little bit out, so-called holdout data set, right? So it's like, I learn from this part, and then I test my knowledge on that part. So that way, there's a fair test, and there's no contamination. Otherwise, it's like somebody gave you the answers, and then you look puzzled, and then you tell me the answer back, you know? So it does that thing automatically for you. And I think the split is 80, 10, and 10. There are other things here, but we don't need to worry about that. When you go to this analyze thing, what it does is basically grabs that data, sucks it in, and does an analysis. A very simple, lightweight description of what the different columns in your table mean. So the name, the type, what percentage of missing values there are. So real data sets, they're always, not always, but very often missing values. If they're created by humans, sometimes humans don't do the work. They just don't type the thing in. They don't press the button that they're supposed to be pressing, right? Or maybe this is an automated system, but the sensor went down, it burned out, right? Maybe your machine crashed. All missing values arise in all kinds of ways, in all kinds of domains. It also does a few simple things like distinct values, just so you get a sense of how much variation there is. Any kind of invalid values just don't fit. The correlation with the target, and maybe some kind of mean standard deviation, some simple aggregate summary statistics. Because this is categorical and text variables, it means the standard deviations are undefined. Because those are numerical concepts, right? So this analysis is not particularly interesting. We go to the training page. There's a button that says train the model. I already pressed it before I came here. You can basically select for how long is it going to do that whole big brute force, fit all the different models, try all the different patterns. and it goes in 1 hour increment, 1 hour increments. That's something specific to Google. DataRobot, for example, doesn't impose that limit on you. You could just fit 1 model or fit 60 models, right? Up to you. Here, they again, I think the user interface is so abstract that it's like just pick time, you know? When it did this whole thing in the background, this is what comes back. And it is basically a summary of how well the predictive model does. And there are a couple of things to pay attention here. So our target is the category. There are a few measures for it. Maybe the easiest one to explain is this accuracy. How do you calculate accuracy? You put a text message in, it says spam, then we go and look up the answer. Was it spam or not? If they match, that's 1, that's accurate. If they don't match, that's a 0, it's inaccurate. Then you do that thing for 1,000 instances, you get a percentage. That's accuracy. So that's pretty good. So it's, at least in this data, it was really good at distinguishing the two. Maybe this is kind of fabricated. This came from a competition. Maybe it's too easy for the real world. When you deploy this thing, actually the accuracy is likely going to drop because people innovate, they change their messaging. The people who are sending the spam campaigns, it's not the same thing all the time. So sometimes you need to rebuild the models. So these accuracy metrics, don't think it's like forever kind of thing. All of this other stuff here gets a little bit more into the weeds of explaining how to breaking down the accuracy in terms of, for example, true positives and false positives. Because you could say, well, what kind of error does it make? If something is spam, do I typically say that it's spam? And if something is not spam, do I still keep saying that it's spam? Right, because you can basically catch all the spam like that, but then also generate a bunch of false positives. Or you can inversely say, miss a bunch of spam, but avoid, let everything through, right? So you have this little threshold that you actually have to pick. And that's what this thing here is. And then basically, the threshold induces a trade-off between true positives and false positives. Once the model is built, it basically, there's this chart here, the ROC chart, which is on the right-hand side, and it has the false positives here, true positives here, and guessing randomly is a diagonal line. Perfect performance is in the upper left corner, and you see it kind of hovers around there. And when you're moving the threshold around, you're moving along this kind of a curve over here, trading off. So if I move down here, I make a lot more false positives, but I pick up everything. If I move down here, I have less false positives, but I then start missing something, right? So it causes these kind of trade-offs. Finally, if you like the results, if you think that performance is good enough for you in your domain, we can deploy it. So they have this predict thing over here. There's batch or online. So the batch thing, you can upload another file. It will go score the whole data set, and then you can download a CSV file and look at it and do some other stuff with it. That'll be batch. And you'll send it to BigQuery or cloud storage, or you can grab it out of there. But what's more interesting is this online prediction. So that's the API endpoint. When I clicked it, it activated in the background. If you were going to do, let's see. So it actually nicely generates for you a curl instance if you wanted to test it yourself, a terminal or something like that. But we don't have to do this too complicated. API keys, all the other pain. They give you this very nice interface. You can submit a new piece of text and just say predict. You have something coming out over here. So you can start actually testing it immediately, interactively, to see if it makes sense. If it does, then give somebody the URL, access token, and it's good to go, right? So that's one example. The other one I have is for sales. It's very similar, but what I highlight here is the data gets a little bit more complicated. So you have more variables here. So the data set is sales of properties in New York, where you record what borough is it in, what lot is it in, how many ground square footage there is versus overall building square footage, how many rooms it has, what's the split between residential and commercial, all those kind of things. When was it built? And you have a sale price. So you have a sample of sales. And suppose you want to invest in real estate, and you want to go out and examine other boroughs and other properties and see what the market price would generally be for a particular kind of property, in particular kind of location. And maybe you could find something like, wow, you can have this big building with commercial zoning, potentially sold here for a cheap price. Sounds like a great investment. So you can create a search tool for yourself with a model like this to look for investments. The tricky thing here is to think through the data types again, because what it's learning is this relationship again between the inputs and the outputs, and if it's the wrong type, you make it more difficult. So this is where kind of domain knowledge comes in a little bit, like boroughs, for example, is a categorical variable, even though it's marked with numbers. You know, numbers just are often used as categories, like jerseys, football players, right? Number doesn't, it's not a really numerical concept. It's just a label. So you have to think through that, identify your target again. It will do the analysis. This one is a bit richer, because there's different types of information. One new thing is this missingness. You can see that in this particular data set, the apartment number, for example, was missing 77% of the time, right? Some other things, the easements, which are basically special applications of the property. The square feet, about 30% or so, right? And then you have how many distinct values. And now, because you have all this numerical stuff, you can actually start calculating correlations. So it just gives you a sense of how are things related to the variable we want to predict. And one of the higher ones is the borough, right? New York, where you live, matters a lot, right? Go to the train thing, press a button, run this thing, stuff comes back. Now, because we switched from a categorical target variable to a numerical one, from ham and spam to dollars, these metrics adjusted, because you measure accuracy differently depending on the type of data that you have, right? And in this case, what the algorithm was optimizing for is this RMSE, which is root mean squared error. All it is you want to guess how old I am, take a guess, we compare it to my actual age, we square the difference. That's a measure of how inaccurate you are. And we can do this across the whole room. You guys all guess my age, and then we just average the numbers, take a square root of that. That's it. It's a very simple metric, but it will tell us overall how accurate is the rule. And you can think of it overall how accurate is the algorithm across all the different properties that it has seen. So it's a kind of a statistical concept. One nice thing, again, it also tells you which variables are most important. So sometimes you wonder, well, why is it predicting the things that it's predicting? What's driving the predictions? And this is a very simple plot for it. Basically, the way it works out is what you can do is you take your table of data, you pick a column to figure out how important it is, you can randomly shuffle it. And then note what the prediction will be after you shuffle it, compared to before you shuffle it. And that tells you how important the variable is. If the variable has a very strong relationship to the target, and you randomize it, you're going to break the relationship. And your predictive accuracy will go down significantly. So that's the logic behind this plot. And so basically, if you start saying that this property actually was not in Manhattan, but it was in Brooklyn, that makes things bad. Same thing for feet. It makes sense, bigger properties, bigger sales. Year apparently is important too. And you see the zip code, address, borough, they are, of course, intercorrelated, right? Same thing with predict. We can do batch or online. This is the online thing. Again, gives you a nice interface here. Now you have, of course, more variables here to insert. Same thing, we could say, for example, that the property actually had, let's say, a total of 4 units. Now, you have to be mindful of the relationships within your predictors themselves, right? I just raised the number of units to 4, but in our data, total units were number of residential units plus commercial units. So now I have to go and find here residential units and commercial units, and suppose I add a 2 in here, right? So the logical structure persists, right? Because you're not going to observe an apartment with 4 units, but only 2 and then 0, right? Doesn't make sense. Click a prediction, boom, number appears over here. They're trying, so this, I was surprised by this, that they didn't show this. A lot of these systems don't have any concept of uncertainty in the predictions. It's a very important concept, but it's still missing. But if you actually pay attention a little bit to the numbers, they don't look good. It's inaccurate. So I don't know what's going on there. It's 1.4 million, and this is not close, right? So this feature is still off. So another API, and again, it gives you the request object, curl command. Of course, you can use any client you want for doing HTTP stuff. So those are the 2 examples. AutoML is not a silver bullet. So there's a few things that are really positive and a few things that are negative about it. One great thing for people who want to do some AutoML but don't know the whole data science stuff is the workflow. It just tells you what stages to go through. Put some guardrails in, put some nice automations in, exposes certain things you should think about and other things you probably shouldn't consider. It does data splits automatically, so people who are new to the space often mislead themselves by peeking at the data and using the data multiple times. And basically, again, it's like I gave you a test before the test, and you looked up all the answers, and then you come to the test, you know, that kind of stuff. This is a source of a lot of false hopes that it tries to prevent you from. There's tremendous, it uses, a lot of these things use open source implementations, which have been worked on for a long time. Highly efficient, like XGBoost library would be one example. An amazing library. Multi-threaded, has GPU support now, like just meant to be just to crush problems on the order of 100 gigabytes on a single server, like minutes, you know. Really powerful, and a lot of them have that as a component. Infrastructure management, so most of those have cloud deployments, so you can avoid all the DevOps stuff that goes with this, Dockers and Python environments and all this other stuff, APIs, and so that's nice, especially for testing. Before you start building anything custom, it's pretty amazing actually. And it forces or targets as a final end the path to deployment of value, right? I mean, I work inside businesses, so that's kind of the end goal, right? The ROI, and it sets you up for that path. A lot of projects still fail. A lot of them shouldn't be failing. They fail because, again, the workflow, the good practices are violated, and the goal isn't specified. Hey, we need to put this thing in production, make it, exposing it to other developers or other applications or end users or dashboards or whatever the destination of it is. So AutoML can help with guiding you towards value. A couple limitations. It only has so many models, right? When it does that whole brute force big search, it can't do it for only many things, right? So the constraints are good. The constraints also sometimes don't fit your own use case. So it's a good place to start, but there's no guarantee that it will succeed. Often it fits like 100 different models, and it puts them on a leaderboard, measured using the same accuracy metric. And if you pay attention to the numbers, you're going to see that most of them differ by like a third decimal place. So you've spent a lot of compute resources and a lot of time waiting for basically indistinguishable models. All of them are learning the basic relationship. So it can be very wasteful too. And Google Cloud, of course, charges by the hour. So something to keep in mind. The other thing is, if you have an expectation about how well in your particular domain predictions can get, you have some minimal sort of viable threshold there, probably guided by your experience in that domain. And if you see that the models can't get past it, you're kind of out of luck within these platforms. There's no good way to iterate. There's no good way to drop into deep stuff, kind of deeper details, without leaving these nice abstract user interfaces and just going back to coding and working with data scientists or doing data science work yourself. So hard to debug, hard to iterate. You have to start, it forces you to leave the environment typically. Yeah, AutoML, try it out. It's a good step towards machine learning for anybody who's comfortable with code. Thank you.